Alrighty, today we're looking at lesson 8.3, which is difference of perfect squares. My video for the last lesson took a really long time, so I'm going to skip through parts of the actual lesson from the packet and just kind of get right into the meat of this lesson. So first we're going to jump to the paper. There we go. To look at some starting up examples. So I'm going to begin by warming up, practicing doing FOIL with that. So it's been a little while since we've done this, but it's really not that crazy. What we do is it's parentheses. I know I'm multiplying, and so you should just distribute this first term to everybody in the second set of parentheses. And then once you've done that, you're going to take the second term and you distribute that to everybody, right? It's just distribution, except with every single term in the first one distributing to every single term in the other one. Let's do it. X times x is going to be x squared, right? When I multiply the same variable, I add exponents, so it's an exponent of 1, x squared. X times negative 4 is going to be minus 4x, and that's it for the top ones. And then 4 times x is going to be plus 4x. And then 4 times negative 4 is going to be negative 16. And we're just going to finish this up to get it in quadratic form. I see like terms, negative 4x and positive 4x. They're going to cancel with each other because they're the exact same number, just opposite signs with the same variable. And I'm left with x squared minus 16. So this is the answer after foiling that, or distributing those binomials, multiplying those binomials. Now, we're gonna look at this a little bit closer in a moment, but one thing that I want you to notice is if I have no coefficient, or I guess even the same coefficient in front of my first term in each binomial, in each parentheses set of two terms, and if I have the last number in each of them the same number but opposite signs, what's always going to happen is, because this positive 4 is going to multiply times this positive x, I'm going to get a positive 4. And then because this positive x is going to multiply with a negative 4, I'm going to end up with a negative 4x. So if I have this situation where I have the same number at the back of my two polynomials and they're opposite signs, there's going to be a part somewhere where they're going to cancel out the single variable part. So I'll just be left with a squared term and a number term, and that's important. So what I want to do now is we're going to do the same kind of problem as another warm-up, but this time only with variables. And it might seem kind of weird, but let's just do it, right? So we're going to follow the same steps we did there. I see that I have two polynomials and I'm multiplying them because it's parentheses. And so just like I would normally, I'm going to distribute, but I'm going to distribute each term here into every term over there. So a times a times negative b times a, and b times negative b. So let's go. A times a, that's going to get me a to the power of 2. A times negative b is going to be minus ab. I don't know what a times b is, so I just have to write it as AB, and it was a positive a times a negative b minus ab. And then I'll do the second term distribution. So b times a is going to be, b times a, I'll just write that as it's a positive and a positive, plus ab. And then b times negative b is going to be a negative b squared. And notice what happens here. When I go to combine my like terms, I have a minus ab and a plus ab. So just like we saw on our first example, these two are actually going to cancel each other out, and I'm left with an a squared minus b squared. And this is, like the start of what this lesson is really about, at least the introduction part of the lesson before we get to practice. Here we saw we canceled things out. I'm left with two terms, and I have an x squared and a minus 16. Here, just practicing with variables so we can see the pattern of what's going to happen, I'm left with two terms, and it's a squared term in the front minus a squared term in the back. And that is the important bit. We didn't notice that the first time here, but x squared is a squared term, right? It has a square there. 16 is also a squared term because the perfect, it's, well, really all I want to call it is a perfect square. I'll just mention really quick, a perfect square is a number whose square root is a whole number, right? A number who has somebody squared makes me. That's what a perfect square is. I'm not going to write it out for sake of time because these videos, I think I'm already like 5 minutes in or something. Okay, so this is where I wanted to get to. I'm going to skip that do now because we did our own little do now. But this is kind of the core idea where if I have something like this as the factored form, when I multiply it, it will get me a square minus a square. And if you notice at the start of this lesson, I said this lesson's called the difference of perfect squares lesson. So if you have a difference of perfect squares, where am I? If you have a difference of perfect squares, and this is where we're starting, right? Because we're factoring now. We're doing the opposite of multiplication. If I start with something like this, a square minus a square, there's a real nice and simple, easy way to factor instead of having to do either GCF factoring or a bunch of other work that we'll see in future lessons. Yeah, and so, right, we saw as the examples, when I multiply things like this, I'm going to always end up with, when I multiply like a plus b, a minus b, or 4 plus x, x plus 4, x minus 4, it's always going to end up with a difference of perfect squares, right? A is a perfect square because a times a gets a squared. B is a perfect square because b times b gets b squared. And it's a difference because I'm subtracting. Same thing here. X times x makes x squared. 4 times 4 makes 16, which is what makes 16 a perfect square. And again, it's subtracting. And in general, nice little time-saving rule, especially when you're doing like SATs and stuff like that, is if you see a difference of perfect squares, if you see a square term, a perfect square term, minus a perfect square term, you can just say, hey, I'm going to take the square root of that first term and the square root of that second term, and I'm going to put them into two different binomials. One where I'm adding them and one where I'm subtracting them. So just to like read off of this, in any difference of perfect squares, they will always factor as follows, and here again is like a variable way of showing it. That is, in one factor, you add the square roots of my perfect squares, and in the second factor, you subtract the square roots, what I just said. Let's look at the four examples to start, and then we'll get a chance to do a bit more practice. I think in the next lesson, we'll be just practicing on this. So we're just going to look at questions 1, 2, 3, and 4 over here. This is perfect. Number 1, we already have, go away. Number 1, we already have x squared minus 16 over here. So let's do it. I see two perfect squares, and I know that the rule is you have to square root both of them and then add the two and then subtract the two. So the square root of x squared is just going to be x, and the square root of 16 is going to be 4. And so now I know, following that rule, that I'm going to do x plus 4, x minus 4. X plus 4, x minus 4. And this is the factored form of x squared minus 16. And of course that makes sense because the way we got x squared minus 16 was by multiplying these in the first place, right? To factor, it's the opposite of distribution. So it makes sense that if we're following that rule, we got with what we started with. We got what we started with. All right, let's keep going. I want to make this not take too long. All right, 4b squared minus 25. 4b squared minus 25. So now we haven't seen this get made. So what we need to do is, if we're being asked to factor this, which means we're trying to do the opposite of distribution, there's a couple tricks that we're learning over these lessons to do that. I'm looking at these two terms and I can say, all right, I know difference of perfect squares is a thing where I get the square root of one, square root of another, add and subtract them. How do I know if this is a difference of perfect squares? Well, you just got to check each term and see if it matches. So 4 is a perfect square because if I get the square root of 4, it's 2, right? If I can get the square root of something and it's a whole number, it's a perfect square. Or if you want to think of it another way, if I can think of a number that when I square it, when I say this times this makes that number, that's another way to say it's a perfect square. So 4 is a perfect square because I know that 2 times 2 will make 4. The square root of 4 is 2. B squared, any variable with a even number exponent is going to be a perfect square because I can just take, that variable times itself, b times b, makes b squared. And then finally, I'm subtracting, so it's a difference of at least one perfect square, and the other one, 25. Square root of 25 is a full, nice number, is 5. So this is a difference of perfect squares. So now we can just do it. I'm going to do the square root of 4b squared. And so the square root of 4 is going to be 2. The square root of b squared is just going to be b, and I can check that by saying, well, if I do 2b times 2b, 2 times 2 is 4, b times b is b squared. Yeah, that checks out. And then I'll do the square root of 25. Well, that is 5. That's just, you should know that. Like, square root of 25 is 5. And then you just add these two terms and subtract these two terms to get your factored form. So difference of perfect squares, once you start to get it and know what you're looking for, it becomes really easy. So 2b plus 5 and 2b minus 5. So this is the factored form of this. And again, the way we did it is we said, all right, is this a difference of perfect squares? Yeah, first term's a perfect square. Yeah, the second term's a perfect square. Yeah, I'm subtracting them. So then I just get the square root of each, and then I add them in one set of parentheses, subtract them in the other. That's the factored form. And if you want to be super safe, I'll do this for this, only this example, and then we'll just rush through the last two. You can double check by multiplying, distributing, and if it comes back to the original, you factored it correctly. So I'll try 2b times 2b, 2b times negative 5, 5 times 2b, 5 times negative 5, and let's check it. 2b times 2b, 2 times 2 is 4, and b times b is going to be b squared. That's looking pretty good. Let's do the next. 2b times negative 5 is going to be 2 times negative 5 minus 10b, and that's it for those two. 5 times 2b is going to be plus 10b, and then 5 times negative 5, negative 25. And again, this comes back to what we saw in our, original warm-ups up higher up on the page, where this factored form, the reason it works is because it's going to give you two parts that cancel out, and then you're left with just the two perfect square parts. Oops, 25. I'm sorry, that's so ugly. But yeah, so it worked out when we checked it. Let's do two more examples just to kind of fill this video out. All right. We're going to do maybe just one more example because I think I'm already over like 10, 15 minutes at this point. I don't want to have it be too crazy. And I also want to have enough content for when we're just straight Russian examples. 4n squared minus 1. So we got to ask ourselves, if I'm trying to, again, factor this guy, I know that I have GCF factoring. I can't divide anything out of these, right? 4 and negative 1, I can only divide a 1 out. There's not an n over here to divide away, so I can't GCF factor. So the next thing I would check out is, all right, let me try difference of perfect squares. 4n squared, 4 is a perfect square, n is a even exponent, so n times n would get me n squared, that works. And negative 1, it is a perfect square. Well, 1 is a perfect square because 1 times 1 makes 1. So now we can do it. I'm going to get the square root of each term. So the square root of 4n squared is going to be, square root of 4 is 2, square root of n squared is just n, and I know that works because 2 times 2 makes 4, n times n makes n squared. The square root of 1 is just 1, 1 times 1 makes 1. And now that I have the two square root terms, I'm just going to add them in one and subtract them in the other to get my two parentheses. So it'll be 2n plus 1 and 2n minus 1. And that is it, right? I guess since this is our last example, we'll just double check to show that it works and why it works. But that is difference of perfect squares factoring. We're going to do more practice in the next video on it. But, you know, it's kind of easy once you know where to look for it. The hardest part is really just figuring out, like, oh, this is a difference of perfect squares. And once you know that, it's just like square root of this, square root of that, add and subtract them. Let's just show that this works. So I'm going to, again, do this distribution. Bada boom, bada boom. 2n times 2n is going to be 4n squared. Looking good. 2n times negative 1 is going to be minus 2n. 1 times 2n is going to be plus 2n. You're always going to see these two terms in the middle cancel out. And then 1 times negative 1, minus 1. The two like terms, they cancel each other out, and I'm left with 4n squared minus 1. Now again, just like last thing I'll say in the video, this is the answer, right? This is the factored form. Factored form. That is our answer. If they ask to factor this, that's our answer. This over here is the check to make sure that we did our work right? So you factor it, and then you can remultiply just to see that you got it right. But if you're confident in yourself, that's all you need to have as your answer. That's what you should be boxing. That is lesson 8.3, at least the start of difference of perfect squares. But as always, you need to get practice, see multiple examples to kind of like get a better understanding and kind of see all the tricks that are associated with it. I hope this video wasn't too long.